how do you know your how much is your laptop capability or anything is by basically this maximum system thread I have around 16 core. Some of them have 64, some have 128 as well. So this becomes a very useful for you when you are doing reservoir simulation, because this if the threads and cores are higher, then your simulation becomes faster. Because let's say we are going to work on a dummy model, but when you are going to work on a live project, the thing is that the runtime becomes a bigger issue when you're working on large complex models. And when you go in your future career development, you will see that there are model cells of around 20 millions to 30 millions, like such a large scale model. So your high performing computer must have the same capacity to handle these problems, because if you don't, then you will have to wait for a runtime for a long time. Okay, so we'll just create one. I'm just going to name one because we are going to create a new model. Okay, I'm just going to name whatever, let's say PBL. It depends on what you want to add to your part. Then once it is done, so as you see, before I import the rescue file and all this stuff, I'll just show you what each tab does for you. So one thing is that this is your cases, where you will define cases. As we go further, you will understand that part. Then you have your geometry objects. Geometry objects where you can see your 3D results, 2D results, everything. As well as cross sections, if you want to build a well cross section and see how my properties varying over that period on that place, basically like in terms of X and Y. Then you have wells table, where you can see the wells data, whatever you have wells, basically that XY coordinates, what is the depth, how much kV shift it has happened, trajectory and all these stuffs. Then obviously the well section, where you see the log data, where you can compare your log with your model properties, because that's one of the QC parts of using a static model. Then you have histogram, where you can see the histograms of different properties, how it has spread over the areas basically. Then you have cross plots, where you can see your K by K5 relation, 5K porosity permeability relationship, and see how overall rock distribution has happened. Then obviously normal tables, where you can create your own table. Let's say if you want to have a communication between two different reservoirs and two different zones, basically not reservoirs, you can call it two zones, and you want to have there is a transmissivity happening between there's a fluid communication happening between these two reservoirs, two zones, so you can add that as well. Then the parameter distance, for instance, let's say you could create a polygon around. You can't see the screen. Daniel, can you see the screen? Is everybody able to see, or just you?
Yeah, we can see. But
Yeah. Okay. So obviously that's parameters, distance is nothing but let's say you build a polygon. Polygon is nothing but a shape or size you want to determine, that is polygon. We will come to that. And you want to see the distance, how much the fluid has varied over the period of that time. So you can see that in this part. Then there are different tabs as well. what do you call 3D crossplot. Similarly, crosspots in 3D you can see. VPC is nothing but variation proportion curve, where how the faces has been distributed over the reservoir you can see here. Then you have table, obviously. Then the material balance part is there, and WCD is nothing but it's basically drainage part. Well, worst case drainage part, where you can see how much, which perforation is having the worst production part. Then obviously parameter. Then these are the different tabs you have, and as you see above, these are like, this is a workflow kind of thing. Like you basically build a workflow on your own. You want to create a 3D model, you want to do different things. Basically you can use this already inbuilt workflows are here. For instance, if you click this library option, okay, it's opening. So once when you click that, you can see a lot of different workflows which are already pre-inbuilt. Let's say if you want to build a cubicle model or anything, you can use this as a, see, there are different scripts: fine structure, perforation, transmittivity, RP endpoints, well cross section. So these are the different workflows which are already there. So you can do, or if you want to build your own, you can just use different properties. Like let's say you want to create a grid, so you just click one here. So import grid, create grid. You can create a simple grid here. You just have to double click here, it will automatically import into that. So these are like now the current methods which we are trying to bring into more for clients or clients to use more, because this becomes much more easier. In this one workflow, you can do your static as well as dynamic part in one click itself. You don't have to do multiple times. This workflow can be then used. Can this screen be zoomed? Okay. Okay. 1 second. Just a minute. So is it visible now? Okay. All right. So, all right. So that was that. Then you can have a different what do you call, where you can see all the log files here, how much or what has been done and all these stuffs you can do. Then there is wells, what are the things done in wells. You can see here, if there is error or warning, it will pop up eventually. Then we come to the fluid properties, where you import the fluid data and everything here. Then wells data is there, where you import the well data. Then obviously graphs, where you can see your results. So this is now okay. Now I'll just change the settings, because we are going to do into field settings, so that is easier for us to understand eventually. Okay, apply. You just apply, then the fluid units are converted. Now you go to, the first thing you do is build a grid, because we are going to import a rescue model. You need to build a grid here. So I'll create a grid. I'm going to name it as MG, whatever you want to go. Let's say PVL. Okay. Now we click project, then import rescue file. You select the rescue bin file, open. Okay, so it will automatically import wells, everything from rescue. Yeah. So before this everything is done, I'd like to tell you about the ways we can import files. So basically there are n number of ways you can import files. One of the ways is basically you can build your static model in geology designer and then directly open it in your what do you call model designer. Then the other is basically importing an existing model. So what happens in a basically an existing model is that when there are different cases generated in your different tools, let's say there are different softwares all around the world, you want to use those models created in those software into your tNav. So you can only import the case file basically using a data model, existing model basically. So existing model in the sense, when you're defining a case, you will defining certain parameters, such as porosity, permeability, saturations, and fluid properties, everything. These will be defined. So once we are using a data file, only these properties which are defined in that simulation case you can import. But if you are going to import a rescue file, what happened is that some of the softwares which are used outside, what happened is that you can import all of the properties which were created in it, not just one file. Okay, so a rescue ML is another format of that. Summary graph is basically importing the production part, graph data results from other directories. Then similar to that, import requested result also is one of them. Okay, so this is one. Now that we have imported, we'll just close this because we don't need this one. So the 3D model. So this is how many wells we have. So these are the axes X, Y. Now you can just show a default view like how you want to see. So this is your X, this is Y and Z. And obviously then you can just switch off the axes. And I don't like the axis much part, so I'll just switch it off so it's easier for me to see the whole screen. Now when we come back to the imported data, these are the imported data. What are they? FIVD, so it's basically a dummy data kind of thing, dummy property, like a zone setup. Then this is your permex in the sense permeability in the X direction. Then you have obviously porosity and NTG and zone ID. Zone ID is nothing but, let's say if you have multiple zones in a single reservoir and they are somehow different connected through a very laminar shale, there is chance of communication, but it is very minimum. So you define the reservoirs into multiple zones so that it is easier for you to populate the properties differently. Because let's say one of the zones has highest permeability and the second one has a lower permeability, so then that becomes a bigger challenge for anyone to make the flow behavior or populate it because randomly. Now what are we going to do is, since we have already permex, we are going to use permex. So usually access, so that I'll show you, it's easier. So permeability in X. So we have one direction permeability. Permeability is a directional property. We already know that since you already have used in your colleges and everything. We already have X and we need Y and Z. So usually what happens in normal sandstone or clastic reservoirs is that we assume that there is not much lateral anisotropy in your reservoir. The reason being the depositional environment has not affected the laterally as much as it has affected vertically. So the reservoir is assumed to be similar in terms of X direction and Y direction in order to reduce the uncertainty in our simulation part. So then that's why we use permex and perm-Y same in most of the similar clastic reservoirs. But for perm-Z, there are different things you can use. So there is not just one value we can use. You can say this is a universal value, not like that. If you have a core sample, then it's a good thing, because usually what happens is that vertical anisotropy, or whatever you want to call it, there is a highly change in variation, because variations. So let's say one layer will have a very high vertical layer communication, but the other will have a very shaly connection on top of that, which will restrict the barrier. So if you have a core and you can justify, then you can justify that this is the value I have used in core because of that. But if it is not that, then there's a trial and error process. Usually what we assume is that the permeability vertical direction or Z direction is 10% of lateral direction basically. So that's what I'm going to do. I'm going to build a permeability in Z direction. And why we are building this permeability in Z direction, you will eventually understand when we are going to what you call permeable in defining simulation case. So how do you build a property basically? So the first thing we are going to do is we are going to build a property. And first you do is go to properties, right click, create, type y, okay, then you go to right click, then again show calculations, where you use these are how you calculate properties. There are different ways to calculate your property. There is obviously arithmetic way, block method, or cylinder method. Let's say if you want to do for one particular area, you can define the property in arithmetic method. It's completely overall reservoir is defined. Then you have moving average interpolation, multi-level facing modeling. So different things are there. You can also create a property based on your tables, fault segmented properties, 2D maps. So there are n number of ways you can create a polygon. Based on your polygon also you can create one. Then you have obviously connected components, transformations. These are like different properties which you will use eventually when the requirement comes. But for this normal training purpose, I'm not going to complicate it much, because I want you to understand like what we are doing when it comes to simulation. That's the important part here. So I'm just going to use an arithmetic part. I'm going to define my property as permx into permx. So these are the additions of sum operator, subtraction, multiplication you can use to define your properties. So I'll apply that. I think I have mentioned it as perm y, but it's supposed to be perm z actually. So I'll just rename it. Okay. If you have any questions, just let me know or raise your hand. I'll just answer it at that moment itself. So once this is done, now we have your permeability, porosity, and NTG. So for instance, reservoir, how do we calculate stoip or chip gas in place, or stock tank oil in place basically is based on our formula of pore volume divided by what you call PG. So now we'll go to the fluid part, where we will use the rel pumps, how we are going to use rel pumps and all these stuff. We are going to see that. So black oil, this is one where we can build. Okay, so we already have water here. It's an inbuilt variant as well, so you don't need to do much. So I'll just add an oil and data. Let me just check what is the value, 0.8 I think. I just that value. Okay. 0.86. because this is an important, any reservoir simulation you are doing, fluid property becomes an important part. So now I'm going to explain what is this going to do once I enter the value. So you see, there are two ways you can build a fluid model. One is by importing it from other fluid modeling softwares, and also you can use PVT mod designer we have already in our in our tNavigator basically. But there are ways we can import other PVT fluid models also from, let's say, here there are different software tools such as IPM or Petrol or whatever you want to call it, you can import. And the other way you can build a fluid model is using correlations. So as you have already studied during your college time, like there are different kinds of correlation when we have in our petroleum industry or reservoir engineering. So what are the important factors which are important in fluid modeling is basically you are seeing in the bottom below. So temperature, obviously reservoir temperature is an important factor. Then is oil specific gravity and gas specific gravity, bubble point pressure, and isothermal compressibility factor. So what these values will do is build a fluid model based on a correlation. And what is this correlation based on? Correlations are based on certain assumptions. Like there are different assumptions for each correlation. So there are different kinds of correlation as well as we have. Let's say you have a fluid report from your field, and now you want to create the exact replica of your fluid model based on the reports. You can either directly import the user-defined tables, which you have here, which you can directly import and paste it here and just apply. Like RS, FVF, viscosity, all these data are always available in your fluid reports. Eventually when you work, you will see that these data are available. You can directly enter that, and or you can use correlation to develop the same table. So once I let's say RS, so gas solubility ratio, you have different kinds of correlation. So let's say if you have a correlation of let's say you have a value of around 600 SCF per or 800 SCF per STB of 800 SCF. SCF means standard cubic feet per stock ton. 1 barrel of oil produces around 800 standard cubic feet of gas. So you need to match that lab report as well with your fluid model. So that should be always be your main requirement, that whenever you're creating a fluid model, it should be as accurate as possible to your PVT reports or field, because fluid is an important factor in reservoir simulation, because once this is wrong, everything is wrong basically. Why I am saying is that it will cause a lot of issues when you're doing a simulation. There will be a lot of conversion issue. What I mean by conversion, you will understand when you work on it. The fluid flow will not be as smooth as what we think it is. So you need to match your fluid behavior, fluid reports with fluid model as close as possible. It's not you're going to get 100%, but some of the times you get as approximate result as much as possible. So fluid modeling is an important factor when it comes to reservoir simulation. So what I'm going to do is I have just replaced some of the values here, bubble point pressure 1.733. Since this is a dummy data, it will eventually match. So that then we have also saturated oil volume factor, formation volume factors, as well as undersaturated, because we need to build that curve from which we get. Once I click OK, you will see that it has created a fluid model. So you can see the table as well here. I'll minimize the table. I'll just keep the saturation bands, and I'll remove, let's say I'll keep RSS. Okay, but so this is how a fluid model will be generated based on the correlation we have. Similar to that, we have FVF as well as viscosity, then compressibility also. Now we go to the gas part where we build gas. So I think gases are around 0.73. Yeah. Okay. So similar to oil, we have different correlation for gas as well. So there are dry gas, wet gas. You can build based on correlation based on there are different correlations for that also. Once you click OK, you will generate almost similar. For oil, we had the same thing. I didn't mention, like there are live oil as well as dead oil also you can build. Then you have around live oil with constant RS, means constant gas solubility over the period of time you can build that. So this is how you build a fluid model. Now that that is done, we can go to rail pumps. Rail pumps are an important factors when it comes to reservoir simulation. This will determine how the flow will happen in our model. So we are going to import directly, or you can build also based on correlation. You just have to click here, and you need to, if you have an idea approximate based on correlation, it will generate automatically. But if you have a table, which I have currently, so I'll just import it from here and field, then I'll select that and PVL, then I go to field data, query, and open. So you see, now we just add, we have our rail pump. Alright. So when it comes to rail pump, the important thing you should remember, like I'll try to explain as much as possible, as fast as possible. So we will just, for now, we will just ignore the gas part. Oil becomes an important thing. You see, what this curve shows is basically our transition zone as well as fluid behavior, how it is going to be. This is our oil one, this is our gas one, water one. So you can see the steepness of the curve is determined by the exponents basically. So let's say if your exponent is less, exponent in the sense I mean NW, correlations, if you see there are a lot of exponents, NW, NO, NO, all this stuff. So let's say if my NW is 1, let's say how much we have here. Sorry. So we have around, NW is around 3. So this is how my curve, like if I change it a bit to, you can see the curve shifting upwards. So this becomes an important factor when you're going to do history matching in your future, because rail pump is a very good thing you can play around with, because these are the data which you are uncertain about. When you're taking a core sample, you're not taking the core of a whole reservoir. You're just taking a core of one single sample. And based on one single sample, a reservoir area of 4 kilometers or 5 kilometers, whatever be the length, you can't determine that the same property will be distributed across similarly. So you can't change the exponent, because the saturations are, the rock is the critical opponent water saturation which you want to call is will be the same in most of the parts, but this fluid behavior, what you call flow behavior, you can play with this basically. So in tNavigator we have the rail pump designer as well. For instance, let's say you have a multiple core, you can also normalize these data, and you can see you can build a different rock physics functions, basically rock core types. Let's say I have 4 phases in my model, I can build 4 different rail pump based on my core data. But if you don't have a core data, you're looking at a lot of uncertainties. You have to play with a lot of uncertain factors, and that's where the HM part comes in. So with tNav, you have covered most of the important things, and you guys are it is going to be very useful for you when you go and work, that you have a first-hand experience of how reservoir simulation works. Currently, you will just learn about button clicking, but once you observe the reservoir behavior over the course of time, you will see that rail pump, PVT, these are the most important factors when it comes to reservoir simulation. So now that we have built our rail pumps, we can go to our equilibrium data. Equilibrium in the sense like we have to define the reservoir's contacts. What is its oil water contact? What is its GOC? And how much is the pressure at that point? How will you determine that? In fluid model, yes, we are defining the fluids and all this, but the simulator must understand that this is at this step my water contact is there. Above this is oil, and above this below above this is gas. So for that we use this equilibration data specification. What we have in tNav is like different ways you can do. Basically, you see, you can enter these data if you have already gas, oil, capillary pressure, datum, depth, and all these stuffs. But if you don't have any, you can just use based on the default by grid option, where it will create based on grid depth. So datum depth it is assuming, then it is using datum pressure and all this stuff, and GOC, WOC are defined based on the saturation, all this. And see, you can see that this is how it's behaving. Now we just rename it so that it's easier for you to use in when we are doing the simulation part. Now this is done, we go to defining the gas solubility versus depth. Now that we have a gas zone as well, right? We have defined that there is a gas zone in our reservoir. We need to define how the gas is evolving over the period of in-depth basis. So the values which we can use is there are different. I have it all right with me. I'll just enter that. So this will be around 6. So you see how my gas is evolving over the course of depth, right? So this is one. Then we have also the rock compressibility, like how much the rock is compressible. So we are going to define that as well. So if you have a compressibility data, you can just directly enter, or you can just create default by grid, and it will automatically. This option is not available in all the tools. I worked in some of the tools, but I haven't seen this kind of thing. In tNav, it is available. It's very useful if you are working on a very normal data. You don't have all these data. You can just use this as a parameter, and it will calculate. So now that we have done this, now your fluid model is done. You have built your geometry object, your geometry objects. You have built your porosity and permeability. Now you can see it in terms of how it is. So we will just adjust the bells a bit. Cut trajectory by depth. We are going to cut it a bit. Okay, so these are our wells. I think my voice is duplicating. It's one of the persons. Echoing. Okay. I think there is an issue. Let me just Mamadou Roger, like you know. Okay, thank you. So if you guys have any question, you can just ask in between. So yeah, so this is that. Now we go to wells data, where we will be importing the wells data. So we are going to create one and import it one table. Okay. So bottom on pressure, we have delimitation as tab. Then you just enter it. Your well data is introduced. Now I have removed. So this is one of the easiest way you can import production. You can import it as an Excel file as well as all other stuffs also. The next thing we are going to go is we are going to import this perforation part and one table. You select similarly here, then it is opened. Then you have to remove the delimiter as all spaces, so you can see that my perforations are imported as well. Okay, so perforation is done. Now we have so now we have imported the production. So we have imported our well structure, well perforation as well as completion data. If you have a VLP curves, you can import that as also, because sometimes we have to match THP as well as tubing head pressure. So you can do that also. So what are the things we have done till now is basically we have built our static static model imported. We have built our permix. Okay, then we have also imported our fluid properties. Now we have done with the wells data. Now we need to create a strategy for the simulator to understand like what it needs to done. So we go to this strategy part. All right, we create this, click on this, the time period, then it automatically, based on our history, it will observe the values. Okay, so this is how your strategy is created right now. All right, so now that you've seen that how we have done, now for instance, if you want to know the value of two different zones, what is the volume of two different zones, what we can do is we can just build one property, create region. Okay, and we are going to use a brush 2D. I'll just open a 2D and create axis. I don't know axis. Okay. So we are going to, let's say I want to define a value. So 1, I'm going to define here. I'm going to use a brush to define these parts of my reservoir as one region. So you can just define it as, you can just paint it like you normally do. All right. Okay, now the second part I can just define as 2, then I just take it, I just define it here. So this is one of the easiest way you can define a property. Basically there are different methods also. Since this is just one way, I'm just doing it for you guys to be useful for you. There is also, you can put a property filter, and then based on that, using equation, you can define as a region. Okay, so now that we see to the 3D part, this is how it will look. Like some of the parts are missing because I didn't paint it properly. So this is one region. This is the region property now. Now wells data is imported. Now we have done this. We'll go to case where we will define in stat. This is where you are defining your static part. You select the grid here, then you select the property you want to keep, then you select the property here, double click on it, just double click on it. Then perm Z we have already defined, so the okay, porosity, okay, pore property is already there. All right, then you have, let's say you want to add the region, so fluid in place I want to know, so I'll just add it. So you see the fluid in place part is added now. All right, now for instance you go to black oil, you need to define your black oil, so you set it here, then you go to your rel pumps. Quarry part we have imported here. Equilibrium we need E2 here because we have already defined that. Then we have RSA already, we have rock compressibility as second part. So now that is done, in schedule section you define the schedule is already available here for us. Now we go to definition part where we autofill the values. So these are like keywords which will be generated in your data file eventually when the model is run and everything, when it's initialized and all this stuff. Now we go to minimum pore volume because we need to define some pore volume to our cells, so which is less than that it won't consider in our runs, otherwise it will cause a issue with your runs. So this will be your minimum pore volume, relative pore volume to the cells, otherwise it will even consider 0.01 as a volume and then try to simulate it, which will cause a lot of runtime issues for you also. So once this is done, you have already built your static. If you have an aquifer, you can just add an aquifer here. Fluid is already added. Now let's say if you want to add different things like grid properties that is added, grid tables, like different kinds of tables I told you, right, for zonal communication. So you can apply this, multiplies transmissibility between multi-num region, reservoir pore volume dilation if you want to add. Then that one thing is that there are different kinds of things you can also, if you want to coarsen your grid, you can use this option. Sometimes what happens is that there are a lot of fine scale models, so you need to coarsen it up a bit, so you can use this coarsen to keyword to coarsen it up. Then you can initial fracture, if you are using a fracture model, you can use this part of parameter. Then you have fault, let's say you have n number of faults, you can add them as a variable here and use it as a transmissibility multiplier. Discrete fracture network obviously for fault modeling. Aquifer I told you already. Results output, these are the different kinds of results output. What is happening, first one is basically it will write all the graphs, then restart steps. So each time restart step is nothing but the model is basically running on each state. So let's say if you want to define a forecast case, you need this restart step. So what will you do is it will define the restart step based on your requirements. So how will you define the restart step is you go to restart step, you can define it at first and last date. Additional properties if you need from them, let's say fluid viscosity, all this you can also directly import from them. Even also graph, if you need what are the grades on the graph need, if you need just for first and last date, you can also do that. So that is one that. Then sector modeling, if you have like a large reservoir and you want to just concentrate on one part of the reservoir, then you can do sector modeling. Schedule is obviously there, where you define the development strategy. Then there is our project manager case. What happens in project manager cases, let's say you're building a fluid model in PVT designer, and then you need a well designer for a well model. You can directly connect it to your defined simulation case and it will run based on that. Even the surface modeling also you can directly connect and run. As I told you, workflow also you can run workflow also based on this useful coupling is similar to that. So now what we are going to do is we are going to create case, and what is going to do, it's going to initialize the model. So what it's going to do, it's going to initialize it. So I'll just give replace existing, or you can give a new case also if you want. So what is happening is that my model is initializing. It's similar to you're doing an initial run of your model to see if there are any errors or not in that. All right, so that's what is happening. So it's now checking for licenses of each of the above 5. Hopefully it was there. Yeah, we got it, I think. So once the initialize part is done, you can see calculated properties or graph. Now let's say if I want to see my standard graph, I'll go to Fignum and I need to see my fluid current oil in place. How much is it? 15 million stock tank point. So I can see like how do you know like what is if the static and dynamic part volumes are matching. You need to initialize that first and see if there is an error popping up, if there is an issue in the grids. What will happen is that in this part you will see those issues, like what for instance there you can see that it is asking license update. Similar to that, it will say that this grid has some issue. For instance, yeah. So constructing corner arrays, writing array corners to file. So it will do a pre-check of all the properties which have been implemented in the model. So that is that. Then you can see also the dynamic results. Basically, you can see the calculated properties, how my saturation of oil is distributed overall. So let's say saturation of, what is it? Saturation of oil, I guess. Yeah, sorry, what? Saturation of oil. This is my saturation of oil over the course of how it is distributed overall. So highest is around 0.53, which is here. Then it is going away this much. All right, then saturation of water, obviously, how is saturated populated. Okay, so this one is that. Now that is done. Now we'll just run the model now. It's running, I guess it will take 20 seconds to run. Okay, so now that the run is done, we can go back to our graphs. I'll just minimize the table. Okay, we have our dynamic. Remove that. Now we are going to see oil rate. Second. Sorry. Okay. Yeah, still get some issue. Yeah, just give me a minute. That's some issue with properties. Oh, I forgot to add one parameter here. Okay, and property, let's mtg. Oh, this is an important parameter. I forgot to add it. So, okay, so now I'll just restart it again. It's existing. Okay, and again run. One second, one second. I think there is an issue. Oh, sorry. I forgot to create one important rule here. We have to define a strategy. So you need to create how the historical well controls will happen. Like how will it choose which parameters? So like constraint, like what kind of parameter it's going to, what is the constraint, whether it is a liquid rate or gas rate or oil rate, what it's going to define. I forgot to add it itself. So next thing is you just select the liquid rate here for producer, then injection rate if you have a water injector. So now that we have added a constraint, so what this create historical well control means that you are giving the simulator, like this is my history data. I want you to simulate the fluid similar to what I have in history. Okay, so now we go to case, again rerun. Okay, so I think it will take some time. So is there any question for everyone? Like anyone has any question, you can ask. It will take some time to run, like 5 minutes. We can use this time for some questions if there is any.
If you have a question, you can ask. Raise your hand and ask and get. No one has a question.
I mean, you guys are not able to understand, or is it like if you have any issues, you can just let me know. Maybe if I'm going fast, you can just let me know. I'll try to go slow.
If you have a question, you can ask. Clement, Dominion, if it is a question. So that doesn't mean that you are fine.
It can be any kind of question. You can ask me. It's okay. Yes, you are first.
Yeah.
Okay. All right. You want me to go from first steps so that we have already done that? I'll just show you what I have done till now. Is it okay? Okay. Sure. No issues. So what I did first, I'll just explain it slowly. So first I build a grid. Like you just go here, right click, you create a grid. All right. Then your grid is created. You go to the project, import. You import your rescue file. Okay, or you can import your data file also directly. So the difference between a rescue file and a data file is that, for instance, in a rescue, it's like a static model. You're completely exporting it and directly importing it. So for, let's say, if you're building a model in Petrel or Halliburton or any other software, you can just directly import all the properties and necessary data like a rescue format. It's like very small size format and you can just directly import it. But when it comes to a data file, what is happening is that in data file, it is an already defined case or an already run simulation model. You're just directly importing into in tNav, and then you're going to run it, because the other software was not able to match the speed which is requirement for our fast or for our model. So that's how tNav is ahead of everyone in terms of reservoir simulation. So the first thing is, Once that is done, we already have our FPID, Permex, Poro, and NDG zone ID till now. What we are doing is we are creating additional properties. For instance, Permex is nothing but permeability in X direction. For instance, in this direction. Okay, and in perm y is in this direction and perm z. So what we assume in a classic reservoir is mostly is that the lateral and lateral permeabilities are similar. If we have any logged in core data where it is saying like you have different properties or different what do you call different properties at different points laterally, then you can just use different permeability y also. But most of the case we are going to use permex and perm y as same. But when it comes to perm set, the thing is completely different, because over the course of time when the deposition happens, there are a lot of shale layers, streaky shale slime, shaly sands, and so there are different there are a number of shales. Each layer has different permeabilities or porosities in them. So what happens is that your vertical communication between the reservoir is not as good as your horizontal communication. So that's why in most cases when we have a core data, we use the core data available. Based on that, we use the permex into the value of let's say 50% of permex is perm set in vertical direction. But as a random number, rather than using a random, we are assuming that only 10% of the reservoir is vertically communicating. So we are using 0.1 as a value. And how do we create a property? Is by just clicking right click, create. When you click create and your property is created. All right, then you go to show calculation, you add the permex, you have already 3D grids which has been generated. Then you go to permex, then you multiply with your value, normal arithmetic calculations you are doing here, so you get that. Now your permeability X is defined, Z is defined. Now why I built a region is in order to show that the volumes of different zone. So how you can build this region is one of the way I showed you. You're using a brush and then determining this value and all this stuff. The other way is by creating property filter. Let's say I want to create a property filter. Open filter setting. I want to see one particular layer in this reservoir. So I'll just click change. Alright, so I'll go here. You can just see I can create different grid layers. For instance, I just want 1 to 20 and I need 1 to 30. Okay, and I need all 1 to how many 40. So I can create a property like that. Okay, so this is one of the ways you can create a property filter. And the other way is block filter, where you can create a new block filter, like based on block. So let's say you need 1 to 50. I just need that. So I can have that. Then another 50 here. So see, this is how we are creating. You can define this as one variable by creating a property and saying that this is one value and the other part is 2. So that's one way. And you can also customize your filter. And how do you do that is basically, for instance, let's say if you want to create a custom filter, you can use one of the properties. Let's say my permeability I'm going to use, and I want to have a permeability of 100 to let's say 100 to 3000 as one region, because there is not much value. So we'll say 100 to 200. JK. So do you do apply those changes? So once you do that, it will create a property here. I think the properties value is an issue. So let's say 1 to 200. So why it is not coming up? Some issue is there. Okay, anyways, so this is one of the ways you can create your filters. I'm just going to uncheck, and then you can create your regions also if you want. So that's one of the way. Now once the geometry part is done, we go to the fluid part. So why fluid is important is basically you need to, when you get a static model from a geomodeler, it's basically an empty tank with only water available in it. You need to give oil, gas. If it has gas, then you have to define those gas. If it has oil, then you need to define oil in it. How do you define that? You use PVT modeling. So there are two ways you can build a PVT. You can build a PVT model in other softwares and directly import, which tNavigator supports every kind of tool available there. Or you can just build one on your own using PVT, already available PVT designer, or just basic using correlations. So correlations in the sense is that we already have a lot of PVT correlations in our reservoir in fluid property table. So some of the fluid properties have been, correlations have been added in this. As you can see, RS, saturated, undersaturated, oil viscosity, formation volume factor, gas solubility ratio. So why these parameters are important is basically these are the parameters which are going to build our fluid model based on a correlation, and what this fluid model will be based on the tables which we have. So there are two ways you can build a fluid model. In this also is basically using the correlation or using the defined tables which we have in your PPT reports. So that is one of the way. As you can see, we can add here the RS and all these stuffs. So once this is done, similar to this, you have to build for gas also. And okay, if you have any questions till now, you can just ask me. I'll just answer. If it is still fast, you can just let me know, or you need to go for me to slow. Is it okay? The speed? All right. So you are able to understand, right, what I'm trying to explain here for everyone?
The speed is okay, right? It's okay. And
Yeah.
I think it's okay.
Yeah.
I think
I mean, since I had to cover a lot of things, I had to go a bit fast. So I'll just go slow for now. Yeah.
I think
Okay.
next time probably we can do this. I think 2 days or something, so that you can take your time and and
Yeah,
and
sure.
the next time. Yeah. So
Sure.
so guys, ask questions. If you want to know about reservoir modeling, there's not something that you think reservoir modeling is. Any question that you have, you can ask Ankit. He will help you understand this better. And know that you'll be doing what you did just now as kind of an assignment. So you have to ask him everything you have to ask him. You get it? So yeah, while he's here, ask him anything, how he got into the anything related you want to know about him, his industry, how he manages his day-to-day life as a reservoir engineer. You can ask him. Or if you have any questions about the moderator, you can ask him. He's here for you. And Peter, you don't have a question.
Okay.
Grace, don't you have a question?
Alright, I'll ask them question. Like, let's see who will answer it first then.
You ask them a question.
Okay. Oh. I mean, you keep working on one thing for a long time, you get used to it. It's not mastering. I still don't know a lot of things in this because I'm relatively new to tNavigator. But yeah, I mean, I'm getting used to the things, but I won't say I'm a master of it yet. Okay, guys, I have a question for you. Let's see who can answer it. It's a very simple question. For instance, let's see. I'll give you a hypothetical question, and you guys tell me what will you do. For instance, if you are given a reservoir model and you are told to do a reservoir simulation, but the issue is that your volumetrics are not in sync, then what will you do? The static model volume which the geomodeler is saying is not in sync with what you have in your what do you call, let's say, pressure, which is not giving the right answers. So what will be your way of method you will do? Do you want me to frame the question better, or you are able to understand? If you can just raise a hand or tell me. Okay, so he is asking petroleum geos. Yeah, you should. You can become a reservoir engineer. It's not an issue. You should just work on your fundamentals of petroleum engineering. It's an important part. Reservoir simulation is just one part of reservoir engineering. There is also well testing you can do, as well as operations you can handle. You can build your well models, and you can do spots. Basically, there are a lot of things you can do. Okay, reframe means. Okay, I'll just give you an example. The static volume which the geomodeler is saying, how do you say prove that he is right or not? Like, how do you prove that? Like, that's my question. Like, static volume. Let's say I have a volume of 500 million stock tank barrels. The geomodeler is saying based on his area, thickness, porosity, saturation, and BG. Okay, so he's having a static model, and his volume based on the structure and everything is around 500 million stock tank barrel. Now, how will you accept that? Like, what are the things you are going to do to accept it? Is it understandable for you now, guys?
So you can raise your hand, then I'll unmute you, then you can talk to Ankit.
What is that? I don't see.
Fever, relax. Let Ankit finish the session before you bring all these problems. Okay. Also, you can speak.
Thank you very much, sir, for the session. Me, I would say if that happens, most probably you need to cross-check with the raw data that you were having earlier on before looking at the simulation data. Yes, that's what I would probably do if I was in such a situation.
Okay, good answer. Like anyone else want to try? Give it a hand.
Anyone else with an idea? How do you verify your static model volumes? How do you verify them? Anyone with an idea? Mauricio, Remy, we've learned this during the week. Ruby, Kelvin, Grace, the two Grace, Isaac and Grace Katusimi, James, Hussein, Felix. People should give it a try.
I mean, it's okay. You can just give any answer. It's not an issue. You just think about it. Like, what is the basic part? Yeah. You make your Yes, we do that.
I think that's the answer to the question. She's saying that you make your geological model and fluid properties by PVT modeling. Grace, are you trying to answer the question?
You can unmute and talk. It's okay. You don't need to type everything. Okay, so you're right, but let me just answer you that question. So when a geomodeler gives you a static model, obviously you do QC and all, so the volumetric part becomes an important factor. The reservoir pressure is a very important thing when it comes to simulation. Okay, no issues, Grace, it's fine. So reservoir pressure says like how much you're going to produce, how much the depletion is going to happen. Like based on that, reservoir pressure is an important factor. So I think you guys know about material balance analysis, MBA and all this stuff. So you do a tank model first. So what you do is you build a tank model and see the pressure behavior, how it is in terms of, let's say, my initial in place. I think if you remember the material balance equation, there is a lot of factors in it. There are a lot of variables, and pressure change in pressure is also one of the variables, if you remember. Raise your hands if you can remember the material balance. I see. How many of you can remember material balance? Yeah, see, Rose remembers it. Okay, who else?
Rose, you have a question?
No, they are actually raising a hand. I told them to raise a hand if they remember material balance. So they are raising it for that, I guess.
Oh, okay, that's nice.
Yeah. So about that, I'm coming to that. All right. So in your material balance equation, if you remember, there is a factor called delta P as well as NP minus N, which NP is the produced and N is the initial part. So based on that, you can create a graph where the drainage, underground drainage part, you can plot it on the Y or X axis, and the remaining part on your other plot. So once you plot that, you will see that the pressure behavior, you can see that if my material balance proves that this much of pressure is there in the reservoir, this much of volume is there, then the pressure will support it. The aquifer properties and all these stuffs, you use material balance to justify that volume. So you can't just go blindly when it comes to reservoir simulation just because the geomodeler is saying that this is my volume. You have to verify it. So you have to go back to your fundamentals, which is material balance analysis. So that's what I was trying to say earlier. This is a tool, but as an engineer, if you want to evolve, you need to remember your fundamentals. That is an important part, whether it be material balance, whether it be the porous flow through porous media part, or fluid mechanics, and all these stuffs. These are very important things. So that, to answer the question, the thing which will help you determining is material balance. Material balance is useful in determining your volumes, aquifer strength. You can determine using based on this, because aquifer movement you can determine how much is it supporting your reservoir based on the tank model. So these two part becomes an important factor in your QCing of static model. So I hope you guys understood. Let me go back to the model where I can show you how over the course of time, like, the result is changing. Now I think the run is completed. Okay, so this is our what I did was I told you till the geometry part and fluid properties, right? You remember? So I defined the fluid, then the rel pumps. I imported it basically. You can build your own also. You just need to click plus, and then based on that, you define these correlation parameters like minimum water saturation, maximal water saturation, critical water saturation, then your residual oil saturation, then your rel pump in terms of oil water, then you have water relative permeability, and then NW is your exponent. Then capillary pressure, if you want to define as a variable, you can capillary pressure exponent also you can define. Also capillary pressure, where the point where your saturation, where the capillary pressure becomes 0. So you can define all this. Okay. So the next thing is just a second, I'm getting a call. It's got no issues. Okay, so we go to the well data. So the first thing we do in well data is basically import our perforations. You go to the right hand corner, you click import one table, you just import it. All right, you have imported it. Okay, the next thing is production table also. Similarly, you create one production table. You just click here, create, and you create one production table, and then you import here, similar to one table. All right. Then once you're done that, you go to the strategy part where you build development strategy. Now you have all the data which is necessary for simulation, but the simulator should know like what it's going to do. So that's where the strategy part comes. You build a strategy, then you build the controls. To control, you define the constraints for your well. Constraint in the sense like you're telling your simulator like this is my well and this is producing with this liquid rate. I want you to produce this much of liquid rate for me. So it does that. Once this is done, You just create one here, right click, create rule. You can select different kinds of constraints are there based on your requirement. There is an history well control, then there is a forecast well control. You can do all this. If there is an injector, you can also do injector. So there are different things for grids also. You can do enable well level LGR, means local grid refinements you can do. So this is one. Okay, so once this is done, you go back to cases. This is where you define your simulation case. Now your static part is converted into dynamic part. Now the simulator must understand the dynamic part. What is it, its requirement? For instance, I am going to define what is my grid basically. So NTG defines the structure of it, permix, perm-y, perm-z, porosity defines the property inside it. All right, and then fluid in place is basically the region specification. Now you might ask me, like, how do we determine the saturation? So what it does is in tNav, it basically extrapolates the value when you're defining your equilibrium. So this is how it becomes an important factor. This equilibrium part is an important factor where you are populating the column, fluid column, how much oil is there, how much gas is there basically. Okay, so once you have done that, then you go to your fluids and you set them, like each part, then log compressibility and all this stuff, and then you click here, run. Just a second, I'm getting a call. Okay, sorry. So I was saying that, okay, so you define the fluid, then there is graphs, restart steps, obviously, then schedule, and all graphs, all this stuff you define, and you just click this button. I'll just reload it again, once again. I'll create a new case. It will create automatically, convert into static to dynamic. What it is doing right now is basically it is initializing it. It is pre-checking all the values which I have entered is correct or not, or approximate or not. Once that it passes through that filter test, you can just click on the red button and your model is calculating basically right now. See, you can see it's already 2 minutes, 2% is calculated. 15, 20. This is a smaller model, but some of the times when you are working in the future, you will see some of the models will run around 100, let's say 3 hours, 4 hours, or sometimes 24 hours. So depending on the size of the model. So this is done. So you see, now I'm going to show you the rates, water rate, and since it was a liquid rate, oil constraint, gas and water. We are going to have pressure, average pressure. Now I have all these properties in one graph. I can just split it based on parameters, historical and calculated. I can explain the play out into 2 to 3. So you see, there is a way you can see all the results which you have generated at the moment. That the pressure is dropping from 500 to 400, then the gas rate is flowing. So this is all that. And you can also see the water cut, how it is increasing. Like you see, there is a flat water cut. All right. So this is till now history match part. I'm not going deep into it because it will require a lot of session for you guys to understand like how history match is done. So just to give you a brief idea like what is happening here, I'm showing it to you. So this one is done. Now we go back to our geometry. Now I want to see how my properties are behaving over the course of time for future forecast. Okay. So So saturation of oil, I'll just give a general and enable access. So default view, I'm going to see so this is how my property is. So I'll just show you the proper pressure property over the course of time. Okay, so you can see how it is evolving. So we are going to play it. I'm just going to click play. So once you click play, this is a time player kind of thing. You click here, all step it will take. This is the over the course of time, this is how the pressure is evolving. Like I'll just show you the first one. Just see this, remember, this is how it is in the earlier. I'll just switch off the wells for now. So this is earlier. And you can see the difference, how my pressure is evolving over the course of time. You see the movement is happening. Over the course of time, like this is how my pressure changes. If you look at saturation also, it will change. You can see it on 2D also if you want. This is my first day. This is the in between. This is the same. Fourth day and last day. So my pressure has depleted all around that. So based on this pressure map, or let's say saturation also, if you see saturation, difference between first and last, you can see that initially the higher saturation we had around here, then there was this layer we had saturation, then as you go further the saturation reduced a bit, but in the end what is happening is that all my saturation are not equally distributed right now. My well is not able to produce as much. So now what I can do is I can just give a forecast. So graph, I'll show you the FIPNUM, the volumes. There are different kind of stuff basically. So total production. So what we are going to see is how much production we have how much has it produced till now. So let's take the oil part only. How much oil is it? It's around 194.7, which is how much was our oil? So we had around 13 millions and the production is way less. It's not even half of it.